Hello everybody, this is Tortoise or Želvík in Czech, and welcome to the new Keep Talking Nobody Explodes tutorial. Today we're covering a module called Quaternions. So, this video will have two parts. Okay, the first part will be just explaining what quaternions are, like its definition and what this means and so on. And if you already know that, you can skip that part. In the description there will be timestamp, so you can just click it and move to the actual tutorial. So for now, I will just explain what quaternions are. This is required for the module, at least like a bit, and it's really good to know if you're attempting to solve this module. So, first, I'll just assume you know what real numbers are, because like to get to real numbers we would need to make a really long way. So, assuming that you know what real numbers are, there was an idea to make a complex numbers, which was like, okay, we can have a number, for example Zulu, which is every such complex number will be a plus b times I, for a, b being real numbers and I being an imaginary unit, which is defined as I squared, which I will denote like this, is equal to -1. This equation wouldn't hold for any real number being I. However, for imaginary unit, we assume this is true. And this way, also minus I would be like squared would be -1, but we'll just assume I squared is -1 and we get that result. Okay, and so we have a real part, an imaginary part, and this whole sum is called complex number. So that's how we make complex numbers, which can be displayed in a plane. If you just imagine a 2D plane of complex numbers, then every point, let's say we have axis, real axis, which is horizontal, and we have a vertical axis, which is vertical. Okay, like this. So then every point in that plane would have a real coordinate, which would be the coefficient a of the real part, so just the real part, and then on the imaginary axis we would have the coefficient b, which is a real number, and then we would just multiply it by I, sum those two coordinates and those two numbers, and then we get a complex number. So that's what complex numbers are. And then there was an idea. Okay, could we expand this even further, like not to 2D, which is, but for example to 3D, because like some robots need 3D technology, so we could just explain that like in programs by using such system of numbers. However, it was proved that it is impossible to make a system with just two imaginary units. For example, like a plus b times I plus c times Juliet, j, because it's incomplete. You can have a look at it, but we won't cover that in this tutorial. However, it was discovered in 19th century, I believe, that if we add one more imaginary unit, therefore making it into 4D, 4 dimension, we can actually make a complete system of that. So, like making it the same as complex numbers, we can just expand that and get quaternions. And there are some properties of quaternions that like normal people aren't used to, like the people that don't know them yet. And it's, for example, anti-commutativity, which means that they are anti-commutative. I hope there are two M's. Whatever. If they are not, then well. And what this means is that if we have a times b, then in real numbers it would be b times a. However, that would mean it's commutative. But anti-commutativity means that if we change or swap those two factors, then we have to multiply it by -1 to get the answer. So A times B is actually minus B times A for quaternions. So that's one property. Other property is which we would expect, which is associativity, which means that if you have A times B times C, that is equal to A times B then times C, which is equal to A times B times C. This is still true for quaternions, A, B, C being quaternions. However, if we wanted to expand even further, we would get 7 imaginary units, octanions, I think it's called in English, I hope. And then that system is anti-commutative and anti-associative. But this time we have it associative, so we will not bother with that. However, this is important. And now, what's about the imaginary units? There's a definition that for those units, it holds that I squared is -1 as in complex numbers, j squared is -1 as, so like similar to simple complex numbers, but we have another imaginary unit, and k squared is -1. But now, like, all of those are not distinguishable. Like now j could be equal to k and so on. So we need one more equation, and that equation needs to include the product of all three imaginary units, and it is defined as I times j times k, which is just ijk, is equal to -1 as well. And this way we can now, from this we can derive products of all pairs of those imaginary units ijk. So let's have a look. We'll be using this equation, this one. So if we want to like have a look at what I times j is, then we know that I times j, that all times k, because it doesn't matter like in which order we multiply, because it's associative. Then we know that it has to yield -1. And what times k is -1? Well, k times k is -1, because k squared is -1. Let me just quickly like do this, which is the same, just it will be like easier to see what we're doing. So if we just put I times j is k, then we have k times k, which is -1, which is okay. Therefore, for this all to be true, we need to have A times j is k. And this way, this is k, and which is the equation above, which is okay. So what about j times k? Well, using the same logic, we can first multiply in this equation these two together, and then we get I times something is -1. I times what is -1? Well, I times I is -1. Therefore, j times k is I. And then we have, for example, I times k. But what if we want to use the same thing, we cannot just multiply I times k like this, because it's not next to each other. So we would have to swap these. Let me just copy this equation, or equality. And if we try to swap these, we get j times I times k. Now we swapped I and j. However, we know that this system, quaternions, are anti-commutative. So we need, if we swap two factors, we need to multiply by -1 as well. So this is actually true. And now, using the same logic, if we get I times k is something, I times k is something, then that something times j times I has to be, times -1 has to be -1, because ijk is -1. So this is still -1, but we can just, we get this. We can just multiply both sides by -1, getting j times I times k is 1. And so if we multiply these two, then there's a question, j times what is 1? We have j times j is -1, Therefore, to get the 1, we would have to multiply that by minus 1. So minus and minus, like this. So we know that I times k has to actually be minus j. So j times j is minus 1, and minus that is minus minus 1, which is 1. Therefore, I times k is minus j. And if we want to get rid of this minus sign, we can, because it's anti-commutative, we can just swap those factors, or the order of them, to get k times I is actually plus j. So we have these, and let me just order that so we have ijk as results in this order. And this is what we have for each pair. If we want to, of course, swap the order, we can, and we'll just get the negation of the previous result. So we get these three equalities as well. Sorry, this is k. So that's what is very important for this module. Also, this is very important for this module, the Zulu. And yeah, I wanted to tell you two more things about this actually. First, how to remember these, because like you will not always try to like do this, yeah, do the derivation. However, in the manual, there are mentions like I times j is k, j times k is I, and k times I is j, and so on. So you don't have to worry about it. And if you don't want to be looking in the manual all the time, then there's an easy how is it? I don't know. There's an easy way to remember it. Just assume that we have a cycle ajk, which is alphabetically ordered, and then it just cycles ajk, ijk. If I said a, I meant I. Sorry. So ijk, ijk, and so on. And now, if you now every pair for every pair they are adjacent somewhere in this string. Actually, we need just this, I believe. Yup. So now I times j is adjacent, j times k is adjacent, and k times I is adjacent. And if we just go left to right, then we actually get the positive results of the remaining imaginary unit that is not in the product. Therefore, I times j is k, j times k is I, and k times I is j. J. Sorry. And if we go the other way, then j times I from right to left, j times I is minus k, because right to left is we have to multiply by minus 1, and otherwise the product is just the remaining imaginary unit. K times j is minus I, and I times k is minus j. So that's how to remember it, like the fast way. Okay, I'll leave those here, but I'll get rid of these because we have it on the module. Like these four equalities can be written as like this four equalities, but actually, this is all equal to minus 1. Therefore, I squared is equal to minus 1, which is equal to j squared, which is equal to k squared, which is equal to ijk. Therefore, we can just write it as this. So I'll get rid of it because it's on every module. That's how actually you recognize that it's quaternions. Otherwise, it looks like a number pad a bit. And last thing, we need to know what conjunction is for quaternions. If we have a quaternion, I'll just name it Q since it's quaternions, so we don't confuse this with complex numbers. That's why we okay. Yeah, okay, whatever. Quaternions, Q. And we need to know what conjugative of Q is. So, it's actually in the manual. Actually, not conjugative, it's just a conjugate. Sorry. Okay, so conjugate of Q is equal to the Q, which is A plus. I could have just copied, whatever. However, we need to change the coefficients in the product of imaginary units and the coefficients. That was like poorly said, but I don't know the wording in English. We just changed these signs to minus. So the real part, the a, which is just a real number, remains the same without a change, which is very important. You don't change the real number when you the real part when you do the conjugate. However, you change all the signs before every imaginary unit, ijk, in whatever order. Like this is just convention to have it in this order. So this is important to know. And now, since we have this, we can get into the module. So now the real tutorial begins. So, hello, this is Quaternions. It looks like a number pad, as I said before. We have a set of equalities. I squared equals to j squared equals to k squared equals to ijk, which is all equal to -1. That's how quaternions are defined. And on the number pad, we have always 5 colors. Which are green, red, yellow, blue, and white, excluding clear and submit. Submit is colored in one of those 5 colors as well, and clear, I think it can change the color as well, but it doesn't matter. The color of clear and negate doesn't matter. We can input some numbers. You can see that there are 6 digits on the display maximum, then none more can fit. If we hit clear, we just get rid of it, and if the display is empty, we can get a negative sign there, but then only 5 digits get in. And we can get rid of the negative sign, like here. Otherwise, when something is there, then it just clears. Submit always submits the module, so we can skip that for now. And now, we need a edge work, and then I will tell you what to do. So, we have 3 and 2, and unlit clear, CLR. We have PS2 RJ plate, and we'll have one more plate, which is just parallel, port on it. Serial number is uniform delta 2, Alpha Romeo 2, UD2, AR2. And now we have the module. So the read that expert needs that's actually quite a bit. They need the colors of all the buttons. So let's just put them like this so we see how it is. It's the same as a number pad, so that's how you can remember it. And you can also see it in the manual page here in the little icon top right. You can see that it's actually 7, 8, 9, 4, 5, 6, 1, 2, 3, and then 0. So we read the colors in reading order to expert: white, red, yellow, then green, white, blue, then red, yellow, blue, and then green is for the 0. And we need the color of the submit button, which will actually tell us what to do. And the submit button is white, which is the hardest one. If it's colored, then it's like okay, and it's like 4 times easier. However, if it's white, then we'll have to do one more thing that is not normally needed. So good for this tutorial, I guess. Then what we need to do is read actually all the colors of the imaginary units. Every imaginary unit has one of the 4 colors, which is red, yellow, blue, green. It's never white, because white are the equal signs. And also there's a real number, -1 of course, which is called the remaining 4th color. So we need to have colors for that. I'll mark it like real, then IJK, I guess, or maybe -1. Okay, that's also a possibility. And we need the colors. So -1 is red, I is yellow, J is green, and K is blue. The color of -1 is redundant because if we have 4 colors, excluding white, so just 4 colors out of the module, then -1 is the remaining 4th color that is not given. So you don't need to actually give out the -1 color. But it is good to do so. Okay, now what do we need to do as an expert? So we've got our read. This is our read. We actually need to calculate a product of two quaternions, which are coded in the colors of this manual, of this module. So in this, excluding this row, we have coded two quaternions. Quaternion is always in this. How do you pronounce it? I don't know. It looks like this. So we need the coefficients A, B, C, and D to get the quaternion, because I, J, K are imaginary units. And we'll have two of those. So we need eight quotients, or not quotients, coefficients. Yep. And then we need to calculate the product. So what do we do? Well, actually the coefficients are coded in these colors. And there are some rules which can be actually broken by exceptions. And we have exceptions rule in table 1, I mean table A. So as an expert, first we'll go into table A and just see if the conditions in it are true. So this color belongs to the I or J component, red. Is red I or J? No, it's yellow. So no, none of these are red. It's yellow and green. The bomb has at least one PS2 port. We do have a PS2 port, so this is correct. The bomb serial number contains a letter in the word blue. Do we have BLUE? At least one of these letters? Yeah, we have a U. So this is true as well. And the sum of the two white keys, don't worry about this parenthesis, I'll explain that in a second, is prime. So which keys are white? I know you can see it here, but here, like, it's the corresponding position. So we have 7 plus 5, that's the two white keys on the module, which is 12, and 12 is divisible by 2, therefore it's not a prime. So we got green-blue are greens and blues conditions are true. I mean, exceptions are true. However, for red and yellow, they are false. What do we do now? Well, let's construct our quaternions. We'll have Q1, quaternion 1, and Q2, quaternion 2. And we have A times... Okay, I will just copy this so I don't have to write this all the time, all over again. We'll have these. However, like this will be A, B, C, D 1, and these will be A, B, C, D 2 for that quaternion. And we have to every time we have to have a look at the colors that are coded here or here on the module, and those colors tell us which coefficient is actually connected to which color. So -1 is in red, therefore the real part is coded in red. So A1 and A2 are corresponding to the digits or one-digit numbers on the module that are in red. Therefore, it's an 8 and it's a 1. So 8 and 1. And now, how do we distribute it? One of these are 8 and one of these is 1. Always, except some exceptions, from those two numbers, the greater one is the coefficient of Q1, or I mean coefficient in the Q1, and the lower number is in Q2. If the exception rule for that color is, however, true, then we swap these two parts. And one more thing, since multiplying by 0 would just mean that that component is not present, because 0 times anything is 0, then we treat the 0 as a 10. So we have actually 7, 8, 9, 4, 5, 6, 1, 2, 3, 10. So this is what you have to be aware of, because this number is actually greater than all the numbers above. Actually, because it's a 10, not a 0. So that's what this parenthesis was referring to, because we just take 0 as a 0 if we're doing the exception rule for yellow. So for red, we have it false. Red condition is false. So we take 8 and 1, and 8 is the coefficient of the Q in the Q1, and 1 is coefficient in the Q2, and it's coefficient of the real part, so we use this like this. Now for B1 and B2, that's the coefficient of I part of the quaternion, and we have a yellow color connected to that. So we need to have a look at yellow keys, which is 9 and 2. Yellow has its condition false, exception rule false, therefore we don't swap anything, so the greater one of these two is in quaternion 1 and the lower one is in quaternion 2. So we have 9i and 2i respectively. Now for J's we have green color. Green color is a 0, therefore 10, because this is a 10 as I said. It's it's written in the manual here. So 10 and a 4. However, now the exception rule is true for green, so we swap those two. So this won't be 10 but 4, and this will be a 10. And I'll just delete this multiplication sign so we have it like this, because this still means the multiplication, just like it's shorter. And for case we have a blue. Blue buttons are 6 and 3, and since its exception rule is true, we swap these. So the lower one goes to Q1, it's 3, and the lower one the higher one goes to greater one goes to Q2. So now we have those. Okay, and we need to do some more things. We did already this. This is just assigning the values, so we have the two quaternions. But now we need to modify it. So by modify it, we mean that if any digit from these 8 digits, except of course 10 is a 0, so we'll just take it as, we'll this time treat it as a 0 this time, or otherwise the 0 in the serial number would be treated as 10. Then if we have that in the serial number, we have to multiply that quaternion's component by -1. So what that means is, we'll have a look what digits do we have in serial number. It's a 2 and a 2. We take just distinct digits, so if they are multiple of the same digit, we just take one of them and ignore the others. So we have just a 2. So we need to find a 2 in these coefficients, which is here. That doesn't have to be a 2 if the white keys is a 2, because we don't remember we don't use the white keys here. It's only used in the yellow conditions exceptions rule. So we take the 2 because we have that in the cell number, and we negate it. So we change that plus into minus. Even though there are two 2's, we do that just once. That's also mentioned in the manual. And that's it. Usually there are two distinct digits. We have just one, so okay, whatever. Now another condition: if there are no lit indicators, we have lit indicators, so this is false. Otherwise we would replace Q1 with its conjugate. We already know what that means. We would multiply each imaginary component by -1. If there are no unlit indicators, which is true, we have only lit clear, not unlit anything, then we need to replace Q2 by its conjugate. So we just take Q2, and to create its conjugate, we need to multiply each of the imaginary components by -1. So minus times minus is plus, and now we change these signs. So minus changes to plus, plus changes to minus, and so on. And keep in mind, you do not change the real part in making conjugate. This is still A, this is still A. Yeah, be careful about that. Okay, now we have this. And the last thing, we need to know what do we need to calculate. It's always a product of those two, but we need to know the order, because you know that the order, like the multiplication in quaternions, is anti-commutative. So the order matters in this case. And if the number of batteries is odd, which it is, 3 is an odd number, then we compute the product of Q1 times Q2. Otherwise we would calculate Q2 times Q1, therefore like putting it like this. That's what I recommend, to have the first one you're calculating on the top. But this time it's true, so we have Q1 times Q2. I'll just put it like this so we can see it more clearly. Okay, and now how to calculate it? Well, there are few ways to do it. I mean, smart ways, and it kind of doesn't matter if you have a white submit, and we do. So this time we cannot take any shortcuts, or at least not really significant shortcuts. So I'll just calculate it as normally, so you see how it's done. And then I'll do one more module, which hopefully will not have a white submit, and do that fairly faster and show you the shortcuts. So, how to calculate it? Well, we just take the Q1, which is this. I put it in parentheses. And Q2, which is this, and put it in parentheses. And so it's not too, spread out. I'll just have it like this, and you cannot see it anyways. Well, that's a shame. What if I do this? Okay, I'll just cover the manual. I don't think it matters too much in this case, and I'll try to get it back afterwards. Okay, so let's continue. So since we have 4 parts here and 4 parts here, we have to, multiply every single, I don't know the word in English, but every single of these with every single one of these. So 8 times 1 is 8, plus 8 times 2i is 16i, plus 8 times minus 10j is minus 80j, and 8 times minus 6k is minus 48k. That was 8 times something. Okay, that was the easy part. Now we need to do the same for 9i. I'll put that on the next row so you can see it more clearly again. So 9i times 1 is 9i. That's okay. Now 9i times 2i, 9 times 2 is 18, so plus 18. However, I times I is I squared, and you should already know that I squared is... Can you see it? No? Okay, well, let's put it like this, I guess. Okay, whatever. Let it there, I guess. Okay, so actually I will just close it. Yeah, whatever. We don't need it yet. I squared is it written here anywhere? I squared. Okay, it's not, but it's written on the module. It's I squared is equal to minus 1. So we have minus 18, which is minus 18. Yep. So keep in mind that this, like multiplying two imaginary units, doesn't always need to yield imaginary unit. This is a real part of the number, so be careful. Now 9 times 9i times minus 10j. 9 times minus 10 is minus 90, and I times j is k. So we have minus 90k. And the same, now it's 9i times minus 6k is minus 54, and I times k is, and be careful, that's like going from right to left in the order ijk, ijk, and so on. So we have minus j. So this is minus j, and minus and minus yields plus. So we have it like this. Okay? And this was a plus. I'll just mark it like that. Okay, we can continue. So to next, for Juliet. So we have plus for Juliet, which is 4j times 1 is 4j. 4j times 2i is 4 times 2 is 8. And j times I, that's right to left, so it's minus k. Therefore, we put the minus instead of plus. Now, 4j times minus 10j is minus 40j squared, and j squared is minus 1, so this changes to plus. And 4j times minus 6k is minus 24, but j times k is I, and it's just I because jk are alphabetically sorted from lower to a higher alphabetic position. Okay, so this is this part done. And the last part, 3k times 1 is just 3k in plus. 3k times 2i is 6, and be careful, k times I, if we imagine it's looping ajk, ijk, ijk, and so on, so then ki is from left to right, therefore it yields a positive Juliet, positive in the, like, in the sense that it does no negative sign. So we have just plus 6 Juliet. Now 3k times minus 10 Juliet, 3k times minus 3 times minus 10 is minus 30, and k times Juliet, kj, that's from right to left, therefore minus I, so minus and minus yields plus, and 3k times minus 6k, 3 times minus 6 is minus 18, and k times k is k squared, which is minus 1, so we change the sign. So that's how you actually calculate these, and like this whole sum is the product. But of course, if we are not finished yet, we need to actually calculate the sum. So let's add the real parts first. So those that don't have any imaginary units. So 8 minus 8, I'll put the calculator now. So we have, okay, yep, you see it, and I'll put it here so it's not hidden anywhere. Yeah, this should be okay. So back to this, we have 8, which is a real part, then minus 18, which is a real part, plus 40, which is a real part, and plus 18, which is a real part. So we have these, the diagonal is done, and it yields 48. That's our A of the product in this manner. Now the I parts. So we have 16 I's, then 9 I's, so plus 9, then minus 24 I's, and then 30 I's. So our amount of I's is 31. So we have 31 I's. Now Juliet's, so J's, we have minus 80, then plus 4, then plus 6, and I missed something, and plus 54. Yeah, it should be minus 80 plus 54 plus 4, and then plus 6. But the order of the addition actually doesn't matter in quaternions. So we have minus 16, and it was Juliet, so J's. For K's, we have minus 48 K's, then minus 90 K's, then minus 8, and then plus 3. So we have minus 143 K's. And this is our final product of quaternions Q1 times Q2 in this order. And now, according to the color of the submit button, we have to submit the coefficient of the corresponding part. So if it was red, then we have red as real numbers, so we would submit 48. If it was yellow, we would submit 31, because that's the coefficient of the I component in the product. If it was green, we would submit minus 16, so don't forget about the negation first. And if it was blue, we would submit minus 143. However, it's white. As I said earlier, we can never get a white for our 4 components. So if the submit button is white, we actually have to submit something else. Oh, yes, I think I saw it. It was here. Okay, it's here. If the submit button is white, we need to enter the square of its norm instead. So what's the norm of a quaternion? Well, norm is just, like for real numbers, it's just absolute value. So it's x if it's positive or 0, and minus x if the x was negative. So like the absolute value of minus 2 is just a 2. But for complex numbers, which are a plus bi, we have to use the Pythagoras Theorem in the 2D plane of complex numbers, and we would just get that it's a squared plus b squared, and then square root of that sum. This would hold for complex numbers. And for quaternions, we will do the same thing. Just use the Pythagoras Theorem 3 times in a row, if you want to know like the lore of it. So we would get actually this. Oh, sorry, I didn't want to insert. Yep. So we'll get that the norm of it is square root of a squared plus b squared plus c squared plus d squared, where a, b, c, d are real numbers, being these coefficients. However, since the square root, of course, can be a non-integer number, and we don't have decimal point here, we actually want to submit not the actual norm, but the square root of the norm. I mean, not square root, but the square of its norm. So this squared, and if I square the norm, then this squared, the second power and the second root will just cancel out, and we'll get just the sum of its squares. So now we can apply this here and take the square of the norm of the product of those two quaternions in this order, which is every single word is important in that sentence, and we can just get that 48 times 48 plus 31 times 31 plus, and of course minus 16 times minus 16 will be just 16 times 16, which is 256, and that plus 143 times 143. Again, minuses cancel out, so I'll just won't bother with them, and this is the result. And now we just submit the result. So it's 23970, and we submit it. And the module is solved after that. You cannot interact with it anymore. It doesn't do anything. Okay, that was 41 minutes of this module. Actually, with the introduction of what quaternions are, so it's not that long. Let's do one more example, however not this, because submit button is white. If you want to practice this for your own, I'll give you a quick read and then submit the bomb, and you can get the result from the log. We have 4 and 2. We have unlit mic assay, RCA plate, empty plate. The serial number is 5 Tango 4, Alpha Papa 7, and the colors are white, blue, red, green, white, yellow, yellow, green. I, J, K, and -1 in this order are yellow, green, blue, red. So -1 is red. Okay? And submit button is white, so you need to submit the norm, the square of the norm again. And you can find the answer in the log file, because I will not bother with that. However, just to show, if you submit the wrong answer, you'll get a strike, but nothing resets. The wrong answer is also if there's nothing in the display. That's always a wrong answer. A 0 can be correct. Can it? No, it actually cannot, I believe, because non-components are 0, so 0 will not be ever correct answer. But if you need to submit anything, if you submit it without the negative sign when there has to be a negative sign, it will be a strike as well.
Emergency
okay?
Clear. All personnel, please return to your stations.
So now we have a red submit button, and pay attention that the clear negation button has changed the color as well, but it actually doesn't matter which color it is. So, okay, let's do this module again. I'll just quickly get rid of every single bit of this, I think, except this. We have edgework 1 in 1. We have lit car. We have RJ and PS2 plate. We have empty plate and another empty plate, so 2 empty plates. And serial number is Sierra X-ray 3 Lima Victor 5 SX3 LV5. Wow, what is this? Okay. No, I will not do it. The read of the module. We have blue, white, green, green, yellow, red, blue, red, white, and then yellow. Submit button is red, and our ijk minus 1 is blue, green, red, yellow. So I'll just mark this so we are not confused with this. Okay, like this. Maybe just for aesthetic reasons do this. Now let's have a look at the exceptions. If you want to do this module on your own, then just pause me, otherwise I'll continue. So this color belongs to I or J. Is I or J red? No, none of these are red. At least one PS2 port. Yes, we do have a PS2. Do we have a blue? Yes, we have an L. Sum of white keys is prime. 3 plus 8 is 11, which is a prime.
Emergency cleared.
So
All
only
personnel,
red
please
exception
return
rule
to
is
your
not
stations.
true. And now we need to construct the quaternions. So Q1 and Q2. For Q1, we need to... Okay, first let's start with the real part, which is actually the minus 1, which is given out last. So we can just like swap it into front, so it's not confusing for us. So we start with yellow buttons. Yellow is has its exception rule true, so we need to put the lower one here and the greater one to the Q2. So for yellow buttons we have 5 and a 0. However, now be careful, this is not a 0, it's actually a 10 in terms of coefficients. So taking this as a 10, then 10 is greater than 5. So we here put the lower one, 5, and here the 10, because the yellow rule is true. Now, let's continue to the I part. Blue. For blue buttons, we have 7 and 1. Blue's exceptions is true as well, so the lower one goes to here. So this is plus 1i, and the greater one goes to here. So this is 7i. Again, I'll get rid of these, and the 1 is actually like redundant to write like this. So I'll just get rid of it completely. So just plus I. Okay, now continue to J's. For J's, we have a green. So for green color, we have 9 and 4. Green's exception is still true, so lower one goes here for J, and this is 9J. And last one is red, that's for K. This exception rule is false, so we put the greater one to the Q1. So we have 6 and 2. 6 is the greater one, that goes here, and 2 is the lower one, that goes here. So this is our quaternions template. However, it's not the quaternions we need to multiply yet, because we did only the first part. Now we need to negate the components that have the same coefficient as the digit in the serial number, treating 0 as a 10. So what serial number digits do we have? We have a 3 and a 5. Therefore, we have a look if we have 3 and a 5 here. For 3, we don't have it here because it's white. So we ignore that. And for 5, we have a 5 here, so we negate that. So it's minus 5. We don't have any more digits in the serial number, so we don't do anything else. If there was 0 in the serial number, then we would change the coefficient of 10 to be minus 10. Because that's what the treating 0 as 10 means. Okay, that's it. Now, do we have lit indicators? Yes, we do. Therefore, we are not conjugating the Q1. Do we have unlit indicators? No, we don't. So this is true. So we're replacing Q2 with its conjugate, meaning that we leave the real part and swap the signs in the imaginary parts. So this is minus, this is minus, this is minus. That's it. Now, what do we calculate? If the number of batteries is odd, yes it is. Therefore, we're calculating the product of Q1 times Q2. Okay, otherwise we would have to swap those two. I don't know why I chose to do it here, because I need to do it here, so I can see them. Okay, and now, again, we will just multiply it, and then take the correspondent coefficient of the corresponding component. So, but that would be a lot of work. Like I told you that there's a shortcut previously, and if the submit button is not white, then you can use it. Because now what do we need to actually calculate? Well, submit button is red, and red corresponds to case. Therefore, we need to calculate. So we need to calculate the coefficient of the k component. That's what we need to do. I hope coefficient is spelled like that. Maybe it's not. Okay. So that's what you need to do. So every other thing is like, it doesn't matter to us. We don't need to actually calculate the real part or I, j's. It doesn't actually matter. So we just need to know what numbers like yield something that will add something or subtract from the k component. And we already know that, like from the previous example. We need to multiply every single thing here by every single thing from the other parentheses. But to each component, we have only 4 things that will add to that component. We'll get 16 things total. Like, I'm using things, but I don't actually know like the word in English that explains it. But yes, that's what you need to do. And since there are 16 and 4 components, then 4 things will only need to be calculated to add to that component. So, what actually gives us case? Well, multiplying real part by real part gives us real part, so that's not k. Real part by what will add up to, like, will be adding to our k component? Well, real part times k component will be k component. So, because this would be real, I, j, and this is k. And we don't care about these, like if we are talking multiplying it by -5. So let's just like ignore everything, and let's just say this is its k component, meaning that we will ignore everything else, and this is like a bottom index. Okay, so we can ignore everything else, and now -5 times -2k is -5 times -2 is +10, and it's just k because like real part times k is k. So we have 10k, but that's not the only thing. That's the first thing out of 4. Now we need to use I. I times what gives us something k? Well, I times real part is I times I is I squared, which is real part. I times j. What is I times j? Times j. I times j, it's left to right alphabetically, so it's k. Okay? Like plus k. Alright, so that's what I need. That's the k component. The other one will be something like -j or something like that. So j component. We need k component, so I times -9j. Okay? 1 times -9 is -9, and I times j is k, so it remains negative, like -9k. And that's I done. For j's, we need to again find what to actually multiply to get to the k component. So for j, this times 10 is still j's. J times I, as we already know, is k. However, not actual k, but j times I is right to left alphabetically, so it's -k, but still k component. So we need to multiply j's times times i's. 4 times -7 is -28, and now j times I, as we said, j times I, as we said, is -k. So this is -k times -k. Therefore, the minuses will change to plus. So it's plus 28k. That's for j done. And for 6k, we need to use, again, what do we need to multiply by k to get k? Well, a 1. So we need to do 6k times the real part, because this would give us j's, this would give us -i's, which is i's, this would give us the real part because k squared is -1. So we need to do 6k times 10, which is 60k. And now we just need to add these. So we don't have 16, as I said, things, but actually like numbers or parts or anything. In Czech, it's called člen. I don't know how it's called in English. Like, that's how it's called in Czech. But now we have just 4 because we're doing one of those 4 components. Because the submit button is not white. We don't need anything else. So let's just use the calculator that's here. I just make sure that you can see it, and you actually could not. That's what I have it here. Okay, sorry for that. I didn't notice. So for the calculator, we have 10 minus 9 plus 28 plus 60. We have 89 case. 89 case. And now, like, everything is done. We need to submit 89. Again, if I submit anything wrong, then I'll get a strike. If I submit minus 89, then it's strike because it's not actually 89. But if I submit it correctly, then the module solves and everything is done. Now I cannot do anything more. Okay, so I think this sums it up. If I needed to calculate something else, like not a k component but j component, then I would do the same, but to yield j's only. For i's, and for -1, I would have to take only the real parts. So minus 50 and I times I gives us -1, and this would be -7, so +7. This would give us these two. After multiplying would give us +36, and 6k times -2k would give us +12. And that's then I would sum those 4 like sub-results and get the actual result for the yellow submit button. And so on and so on. This module doesn't have a souvenir, so this is like everything you need to know about it, I think. Here are some like mentions of how to do it. I'll try to explain it. I try to explain it as well as I could. So I hope that's kind of all. Also, you cannot, like last mentions, cannot add any leading zeros to your answer. And 0 is entered just as 0, not as -0. So that's what you should be aware of as well. Otherwise, this just like explains what the keypad does. Okay, so I think this is it. Thank you for watching, and see you next tutorial. Have a nice day. Bye bye.